The methods introduced so far for controller tuning assume that we know things about the process, like gains for the process valve and measurement, and time constants and time delays associated with the process. This is not always the case. Sometimes a controller is installed, and it needs to be tuned based on observations of how the process behaves without having a full model for the process. One method of determining how the process behaves so that it can be tuned is what's called the continuous cycling method. In the continuous cycling method, we set the controller to P-only control. That is, if it's a PID controller, we need to set the reset time to its largest value, or infinity, so that the integral element becomes very small or zero, and set the derivative time to 0 to eliminate the derivative element. Then we set the controller gain, Kc, for the proportional only controller to a very small value. And we introduce a set point pulse. That is, we briefly change the set point and then bring it back to its original value. With the controller online in the feedback loop, this set point pulse should result in a brief deviation of the controlled variable, which should come back to a steady state value. Next, we increase the controller gain and repeat the set point pulse experiment until we've found the controller gain that results in sustained oscillations in the controlled variable when a pulse is introduced in the set point. We call this value of the controller gain the ultimate gain. The ultimate gain represents the stability limit for the controller gain for the proportional only controller. And doing this set point pulse experiment, the objective is to find the stability limit for the controller gain. The period of the sustained oscillations that are obtained when the controller gain is set to the ultimate gain, Kcu, we call the ultimate period, Pu. If we can set the controller gain to a value slightly larger than Kcu, we should observe growing oscillations in the controlled variable. Once we know the ultimate gain and the ultimate period, we can choose controller settings using tuning relations like the Ziegler-Nichols method, that we mentioned in the previous video. For the Ziegler-Nichols method, we can tune either a proportional, a PI, or a PID controller using the settings found in table 12.7. Note that for all three of these, the controller gain is set to some fraction of the ultimate gain, which ensures that the process will remain stable. When integral action is added, the controller gain must be slightly reduced, and when derivative action is added to a PI controller, the gain can be increased because the derivative element helps to stabilize the response. The Ziegler-Nichols tuning parameters for the proportional PI and PID controllers are introduced in Chapter 12 of our textbook, and these are calculated based on the ultimate controller gain and ultimate period obtained from a continuous cycling method. But the ZN method is not the only method of controller tuning based on continuous cycling. Later in Chapter 14 of our text, there's an example that introduces an alternative set of controller settings called the Tyrrell-Leuben settings. Other similar tuning relations have also been published based on the continuous cycling method. When performing the continuous cycling method, we need to watch out for a condition called saturation. Saturation occurs when either a signal or a process variable reaches its maximum and minimum value during the continuous cycling. This will limit the controller output, even though the controller gain may be set to larger than the ultimate gain. For example, if we set the controller gain to a very large value, a valve may open all the way and it can't open any further. That therefore limits the response of the controlled variable. And although this looks like sustained limit cycle oscillations that we would achieve if we had found the ultimate gain, we actually have a Kc larger than the ultimate gain, which will mean that when we tune the controller, we'll have a gain that's too large. If any signal in the feedback control loop is limited by a performance boundary, then this saturation can occur, and we need to watch out for it. After choosing the controller settings, we can introduce set point and disturbance inputs to see how the process behaves. If the resulting behavior is unsatisfactory, for example, if the controlled variable oscillates too much in response to inputs, then the controller could be detuned or made more conservative by reducing the controller gain. If it takes too long for the controller to respond, then perhaps the controller gain needs to be increased. This is called fine-tuning. Many commercial controller manufacturers actually recommend the continuous cycling method for tuning their controllers. However, the continuous cycling method is often a very bad idea. For one thing, the continuous cycling method takes time. You actually have to run the process multiple times with different controller settings to find the ultimate gain by trial and error. If the process contains vessels with a very large holdup, like large distillation columns or large vessels with large residence times, then the responses can be very slow. Time constants can be hours or even days. This makes the continuous cycling method very laborious and time-consuming. Processes that have a lot of heat transfer associated with them can also have long time constants. The continuous cycling method requires pushing the system to a stability limit. If there's some other disturbance while we're performing the tuning, then this can be dangerous. Often it's undesirable to get anywhere near the stability limit. Integrating processes and processes that are open loop unstable usually have an upper stability limit and a lower stability limit on the controller gain. And remember, the process for the continuous cycling method begins by setting the controller gain at a very small value. So we have to be careful because we may actually be starting in an unstable region. Finally, stable first order and second order processes with no time delay actually have no ultimate gain. Now, pretty much all real processes have some time delay, but that time delay might be a time delay associated with an electronic signal that's really only a few microseconds or milliseconds. So these processes would have very large ultimate gains. Finding that ultimate gain can be challenging, and the resulting controller tuning settings may be too aggressive. An alternative to using the continuous cycling method is to use relay auto-tuning or step tests. In relay auto-tuning, we replace our PID controller with an on-off relay, usually with a dead zone. The diagram representing the on-off relay controller is a cartoon showing how the controller output behaves in response to the error signal or the controller input. When the error signal increases, it reaches a threshold at which the controller output is a step to a new value. That step is called the amplitude D, and when doing relay auto-tuning, we want to set that amplitude to a small value so that the controller output makes a very small step change. Then, as the error signal decreases, there's a hysteresis. The relay goes a little bit past the zero error signal before the step back down to the original value of the controller output. This is similar to the way a thermostat on the furnace in your home or the thermostat on your oven work. There's a temperature that's being measured and compared to the set point, and if the temperature drops, say 1 degree or a half a degree below the set point, the furnace comes on, or the heat supply comes on, and it stays on until the temperature is maybe 1 degree or half a degree above the set point, at which point the heater turns off. If a PID controller in a feedback control loop is replaced with a relay like this, the output or controlled variable will oscillate because the controller output will be continuously cycling on and off. The period of that oscillation will be the ultimate period, the same period obtained if we were to do the continuous cycling method. And the ratio of the controller output amplitude to D and the observed process output or controlled variable amplitude A can be used to find the ultimate controller gain, KCU. Once we know PU and KCU, we can again use controller tuning relations like the Ziegler-Nichols settings. The advantages of doing relay auto-tuning is that no trial and error is required. This can be done in a single experiment, and only a small number of oscillation cycles, or representing the time PU, need to be obtained. Furthermore, because the relay can have a small amplitude, this obviates pushing the process to a stability limit. Finally, this relay auto-tuning can be easily automated. Another online tuning method that can be used is called a step test. To perform the step test, we introduce a small step change in the controller output signal, and then observe the response in the controlled variable. We can use methods from Chapter 7, which we didn't cover, to develop an empirical process model based on how the process responds to the step input. If the process is a self-regulating process, that is, if the differential equation describing the behavior of the controlled variable in the time domain has a negative contribution from the controlled variable, then the process should come to a new steady state. For non-self-regulating processes, such as integrators, a small step change in the controller output may lead to a continuous deviation in the controlled variable. Parameters such as time delays, process gains, and dominant time constants associated with the approach to the new steady state can be obtained by fitting the controlled variable to simple process models. You can read about the step test in section 12.5.3 of our text if you're interested.